clearly, even after doing all of this and inverting the channel, right, I can't still cause a current to flow through this device because there is an oxide on the top, right. So somehow the gate has created some free electrons, but I can't do anything with it because there is an oxide on top and current cannot flow through the oxide. It's an insulator, and therefore we straight away go to what is known as the 4-terminal device, that is my MOS transistor. So what do I do now? I start with my same old MOS capacitor, okay, which basically has the metal and then the oxide and then the substrate and so on. This is my gate, this is my body. So now I add 2 other diffusion regions to the left and right of this structure in this form. Okay, so if this is a P substrate, then I will add an N plus diffusion here. Okay, what is N plus? It's basically N plus is N type semiconductor with large doping, which means Nd is nearly 10 power 17 to 10 power 18 per centimeter cube, typical number. Okay, 3 orders of magnitude more, 2 to 3 orders of magnitude more than the substrate, right, or the bulk. This is basically my bulk or body again. So this concentration is Na, this is Nd, and so on. So now I go ahead and do the same exercise. I apply a large enough potential. I am able to invert the channel by first creating immobile charge carriers here, and I am also able to simultaneously generate some free electrons with some concentration out there. Okay. Now if I apply a lateral electric field, right, the vertical electric field is actually creating the inversion charge for me. If I now apply a lateral electric field, then I can cause these free electrons to move, correct. So this guy, okay, let me say I'll ground this terminal without loss of generality. I'm picking one and I'm going to ground it. Okay, this I will apply a potential Vd. Okay, this is called the drain and this is called the source. Okay, so now if I apply a drain voltage, right, across these 2 terminals, clearly that potential is going to drop across that entire channel, right. So if you look at the way this is happening, I have this going as X, right, and I have a potential in my channel at a distance X. I'll consider a small portion dx here. Okay, so what is the potential here? I am going to call that potential as V of X. So what is V of 0? Yeah, 0. V of L, right, where this is L. Okay, as usual, it is Vd. Okay, so now what is the amount of inversion charge that is available for conduction in that small element dx with width w. Yeah? See, that thing is already at a potential V. Over and above that, I need VGS minus VT. VG minus VT, that can cause an inversion there. So therefore, the net charge that is going to be available, Qi prime, will be what? What did we say earlier? It is minus Cox prime into Vg minus Vt minus V. Okay, because what's happening is at the source, the potential is whatever Vg minus Vt you apply, you will get that much of inversion charge. But as you go, that potential is going up in the channel also. So therefore, you will have Vgs minus Vt minus V. Therefore, if you look at the elemental charge dq, right? No, this is q. Let me call it qi actually, because I want the charge per unit area. Therefore, the dq prime should be what? It is just qi prime, qi into the area element. What's the area element? Yeah? W into dx. Right? So therefore, I have dq prime is minus Cox into Vg minus Vt minus V into W times dx. Right? So I just differentiate with respect to time. This has to be, this has to be a current, and this is called a drain current. Okay, equation of continuity says that the drain current has to be the same through the channel. It can't be different. So it's not going to depend on the position, right? Otherwise, you'll have charge accumulating in one place. Okay, so therefore, I can, and this dx by dt, what is this? This is basically drift velocity, right? Therefore, the drain current can be written as minus Cox into Vg minus Vt minus V into drift velocity. Now, what is drift velocity? It is mobility times electric field, right? So if I apply an electric field, right, the thing cannot just arbitrarily accelerate through the lattice, because now there are a lot of atoms sitting in the lattice. So the electron will have some mean free path, it will collide, then some recombination will happen, and all that. There's a a continuous generation recombination process that happens. So therefore, it's not that the electron can just accelerate as if it's a free path, and therefore it gets related to the electric field through the term called mobility, right? So if you look at the drift velocity, this will be mobility of electrons into the electric field E. Okay, and obviously this is minus mu E times dV by dx. Okay, and wait, there's a W here. Okay, therefore I am now going to say ID equals plus, okay, I think the right notation is mu n. Let's just keep that, mu n. Okay, mu n Cox into W into Vg minus Vt minus V into dV, and dx, I'll bring this side and I can integrate this 0 to L. This will go from what? V will go from 0 to Vd, and therefore Id into L, because now Id is not a function of X. Okay, it's uniform throughout the channel, and therefore Id comes out of the integration. Id into L is mu n C ox W into Vg minus Vt into Vd minus Vd squared by 2. Therefore, the drain current is mu n C ox W by L into, I will now reference it to the source. I said that the source was grounded, so it is just Vg Vd. I will make it more general, Vgs minus Vt into Vds minus Vds squared by 2. Clear? Any questions here? So the current is actually a drift current. It's not a diffusion current like it's in a PN junction. In a PN junction, the minority carriers actually diffuse. Here, majority minority might be confusing, because in the channel the electrons is actually a minority, right? So forget about that. But it's a drift current that is causing. So that's why the relationship is linear or quadratic with respect to applied potentials and not exponential. PN junction is exponential because of the diffusion component, right? This is a drift component that is causing the current. Clear? So now let's see what happens when my VDS keeps increasing. Okay, I'll just keep increasing VDS. At the drain, at the source end, what is the net potential? At the source end, the gate minus the potential at the source end, what is it? Huh? So at the source, Vg minus Vt, right, will cause inversion, right? So effectively it's just Vg minus Vt that is able to cause inversion there. Yeah, my question was ill-formed. Okay. At the drain, what will happen? Vg minus Vt minus Vd. Now if Vd goes above Vg minus Vt, what happens here? This term becomes negative, right? Which doesn't make sense, because basically we are now going below the threshold voltage, which means there is not enough inversion charge there, right? So therefore what happens is the current quadratically goes up until a certain point, and after that the current just saturates, because at the drain end you cannot have this term going negative. Okay, so the channel sort of, what happens is they call it a pinch off region. Okay, so if I have my drain, source and my oxide and gate sitting here, as I increase n plus, as I increase my Vd, the electron concentration will be like this, free electron concentration. It's non-uniform. At the source end, it's going to be higher because it's just Vg minus Vt there. But at the drain end, it can sort of pinch off beyond a point, and if I continue this process, it will just pinch off like this. Okay, this is a very crude picture, but effectively the point is that the current just saturates. Okay, and therefore the ID will simply become mu n C ox W by L into VGS minus VT. VDS, the maximum value is VGS minus VT. Okay, so minus VGS minus VT the whole squared by 2. Basically what I am saying is that VGS minus VT minus V should be greater than 0. Only then you can have an increase in charge at the drain end. It can happen only till V is less than VGS minus VT, right, or VD, sorry, VD is VDS actually. VDS is less than VGS minus VT, right, and therefore this current, if you simplify this, will become W by L into VGS minus VT the whole squared by 2, and this region quite obviously is called saturation. Okay, and the previous current equation was basically called a linear region. Okay, we'll look at the plots in the next class, but if you neglect this VDS squared by 2 for small changes, right, around something in the analog domain, this is basically, it operates in a linear region, it behaves almost like a resistor, okay, by neglecting the VDS squared by 2 term. Okay, of course there is no dependence on VDS in saturation region. Okay, so I'll stop here. In the next class we'll look at the IDVD plots, IDVG plots and so on. Thank you.